In this lecture we will discuss about dynamic devices. We have already discussed about passive and dynamic devices very briefly earlier. So, now we will go into details of how these function and so on and so forth. There are several effects which can be used to control the properties of integrated optical devices. To name some of them are Thermo-optic effect, Electro-optic effect, Magneto-optic effect, and of course nonlinear optical effects. In all these cases, the properties of the waveguide or the substrate are dependent on the external field that we apply to this waveguide. Just to take an example to start with, of course, in all these cases we need materials which have these properties. For example, if you want to use the electro-optic effect, we need a material which has got electro-optic properties. That means, just to give an example, in the electro-optic effect, the waveguide properties are dependent on the applied electric field. So, the material needs to be have that such a property. By applying electric field, we should be able to change the properties easily. To start with, let us look at thermo-optic effect. Thermo-optic effect essentially means the change of the material properties with applied heat. You can heat the material and then change the optical properties. In particular, we will look at the refractive index of the medium that can change with temperature. So, there are several materials which have these thermo-optic properties to varying extents. In fact, most of the materials properties are dependent on the temperature. So, we can make use of the temperature dependence of material properties for creating optical devices controlled by temperature. But of course, different materials have different effects, different are influenced to a different extent by temperature. So, if the material responds very well to small changes in the temperature, then that will be much more effective. So delta n is a refractive index change of the material with the as a function of temperature. So, thermo-optic effect implies the change in the refractive index of the material with temperature. To take an example, let us consider a device. Let us call it as a optical switch based on thermo-optic effect. As an example, I am considering the interferometer, the same example that we have discussed earlier. An interferometer made in glass, I will take glass as an example. Let us call it a switch. I will try to explain the function of a thermo-optic switch. This is the basic interferometer on a glass substrate. So, the substrate is glass. just to illustrate, and we would like to heat the waveguides by putting electrodes like this. This is an electrode. There can be another electrode on top of this if you would like to heat the second part also, or the electrodes could form a part of the circuit to heat. For example, one of the waveguides can be grounded and a voltage can be applied to this electrode. Typically, if I can later on we would look at the technological issues where how you can form the waveguides in various substrates. In the case of a glass, for example, you can form by diffusing silver into glass. So, one of the typical process for glass is called the ion exchange. Silver ion exchange in glass is a typical process. So, we are, and you can have an aluminum or titanium or electrodes which can be heated easily by applying currents or voltages. So, you may also have to have a circuit to this can be called as a load, resistive load you can have to control the amount of current that you pass through this. So, the electrodes could be heated by passing current and the refractive index changes with the temperature. There could be other configurations. This could be a different electrode with this the circuit being made like this. One end you ground it, other end you apply the voltage, and here also you can think of applying only to this electrode and this will get heated independently. From the functioning of interferometer, you know that the phase shift can be given by e power I phi, where phi is the phase shift, and this could be a different phi. Phase shift in this could be different due to the temperature change. We can relate, for example, the phase with the propagation constant 2 pi by lambda into refractive index, effective refractive index of the waveguide to be the propagation constant multiplied by the length of the electrode. So, here the effective refractive index is a function of temperature. So, we can expect the phase shift to result in the intensity change. I out, if you think of input here and output here, we can say that output is dependent on the phase shift. As you know, for the interferometer we have output equals I in. Maybe let us look at only the magnitudes of this. You get in terms of cos square delta phi by 2. So, depending on the phase shift delta phi, we can have the low or high intensity at the output. For example, when the temperature is applied, the output can be 0, and when there is no temperature applied, the output could be maximum, or let me say 1. So, when for T not equal to 0, let me say they are identical, and so the phase shift is 0, and for some value of T, say 80 degrees or so, output is maximum, and we can switch between 0 and 1 by switching between 0 and 80 degrees. This could be called as a binary on off switch using thermo-optic effect. So, we need to understand how much the temperature affects the refractive index change. So, for that purpose we need to know what is this function. In the simplest case, we can say the temperature coefficient of refractive index as a function A plus Bt, where A and B are coefficients and T is the temperature, maybe temperature difference. Most of the time T0 is the ambient temperature or the bias value, and with respect to that we measure the T, and you can say that the refractive index changes with the temperature as follows. We can also plot a graph between the delta T and delta N. For example, if the temperature increases, the temperature can increase or can increase the refractive index or reduce the refractive index. If you say that in the given range of operation the temperature is changing refractive index linearly, say for example 1%, we can find out the coefficients A and B and use it to design a thermo-optic switch. One of the limitations of thermo-optic effect is the speed. So, it depends on the speed, the switching speed, the speed with which we can shift from 0 to 80 degrees. Most of the materials will take certain time to relax between 0 degrees and 80 degrees, and so the speed of switching is limited. If the time required to switch between 0 and 1 is given, say for example a few microseconds or milliseconds, we can calculate the pulse rate with which we can modulate this. This is a switching diagram where you can switch between the 0 level and 1 level. Of course, there will be a small time delay, and switching back also will have a certain time delay, and based on this we can calculate what is the maximum data rate we can go. So, typically it is of the inverse orders. Suppose if the switching speed is say 3 dB, switching speed is some Tp, then we can go for switching speeds or frequency of on off modulation of the orders of 1 by Tp. Now, let us look at another effect which is most popularly used in integrated optical devices, called the electro-optic effect. In a simple way, we can say the electro-optic effect consists of changing the refractive index of the material with applied electric field. So, there are several materials which have got electro-optic effect, that is changing the optical properties of the medium with applied electric field. Typical one, the most popular one is the lithium niobate. So, a few properties of lithium niobate have to be considered first, even though we may not go into finer details of light propagation in anisotropic materials. Lithium niobate is a typically anisotropic material. Which means the properties of the refractive index properties of the lithium niobate vary with direction. So, typically in an anisotropic crystal, if light propagates in one direction, it has got certain refractive index called the ordinary refractive index, and if it propagates perpendicular to that, it has got another refractive index called the extraordinary refractive index. In bulk optics, simply call them N ordinary and N extraordinary, but in the most general case we can say that this is a tensor. Refractive index is a tensor. Or the relationship between the refractive index and the applied electric field can be expressed in the form of a tensor. So, we can express it as follows. We can also express the refractive index as a function of a Taylor series. Refractive index, let me call it, let us in the most general case let me call it, if you have electric field has different components Ex, Ey, Ez, and Delta n also has several components. So, the refractive index delta n can depend on any of these or more than of these. So, we can have delta n in x, applied field in x direction and refractive index changing in x direction. We can express as a matrix y, delta n changing in the z. These are all the different coefficients of the refractive index, delta n xy, delta n yz and so on. So, we have a matrix which will express the relationship between delta n in terms of several fields. So, this is a tensor called electro-optic tensor. So, such material properties could be expressed as tensors in many other cases. For example, if magnetic field is applied and refractive index changes in different directions, the coefficients which express this can be called as tensors and represented sometimes the matrices, but more extended mathematical forms. So, in the present study we will not go into details of how the material properties vary with applied field or how it should be calculated exactly, but we will try to take an applied approach where we express the refractive index as a function of electric field in various ways and see how it could be applied to practical devices. Of course, if you look at the notes, some specific examples of refractive index variation in different directions and applied field are given. So, first let us call it linear electro-optic effect. Linear electro-optic effect means delta n is a function of electric field alone, and if delta n is a function of the square of electric field or the intensity of the field, we can say that the intensity is proportional to E square. So, if the refractive index is proportional to intensity of the electric field, then it can be called as a quadratic effect. Or in general, if the properties of the medium depend on the fields that are within the medium, all these fall under what can be called as nonlinear effects. And if the medium properties do not depend on the field, in particular the field that is propagating, we are in the linear regime, linear property, linear effects. So, in the specific case, I will just give a small formula which is useful to express refractive index profile as a function of electric field. So, in the case of lithium niobate, we have this R, this can be called as the electro-optic coefficient. I will use some other color too. There are the matrix forms, more specific case R33 is one of the matrix coefficients which is very useful and which has got a large value. Similarly, in the case of other materials like gallium arsenide etc., we have other coefficients like R41 etc. So, this is a very simple formula which can be used to calculate what is the change in the refractive index when you apply electric field. If the electric field is applied using a electrodes, for example, if this is the waveguide, this is another waveguide, and you apply the electric field to these electrodes, I will draw a proper picture later on. there is a small gap between these fields, and if the voltage applied is V, we can express E in terms of V by D. Of course, we have to solve the electrostatic problem to find out what is the actual nature of the field, but this is a D is the gap. Based on that, we can improve upon this, and usually you include an additional factor called the overlap integral. I will put it somewhere here. Overlap factor or overlap integral to express the effect of the electric field and optical field. It depends on the field distributions. Distribution of the mode field and distribution of the electric field. We will go into slightly more detail in a few minutes. So, let me take up an example of a modulator, which is one of the very common applications of electro-optic effect is a modulator. I will once again use an MZI. This, as you know, is a standard mags and interferometer where you can put electrodes, and maybe let me put another ground electrode also very close by. So, this is a gap between them, and the phase of this can be shifted by applying the electric field. So, delta n is a function of the electric field R33, this one particular geometry R33 into gamma into V by D into n square of cube. So, delta n depends on the applied voltage. So, like in the case of thermo-optic device, we can say that this could act as a intensity modulator, output cos square delta phi. If this is phi 0, phi, and this is phi dash, where phi dash is expressed at 2 pi by lambda into n effective plus delta n effective into the length of the electrode. So, this delta n is an additional factor for phi dash. For phi, you do not have any additional refractive index change, and you have a delta phi depending on delta n. So, this can act as effectively a phase modulator. And of course, we can change the applied field very rapidly, and you can get very high speed modulation. Typically, if you want to go for a very high speed modulation of the orders of several gigahertz, say 100 gigahertz, we can use an electro-optic modulator. So, as you may have noted that this is in the microwave range and high frequency, and you can express the wavelength of microwave that is impressed upon that. This particular example shows a lumped electrode. That means the electric field is uniformly distributed and does not change very rapidly. So, you can use the lumped electrode configuration to study the properties as a parallel plate capacitor, and you can determine or calculate the bandwidth of the operation and so on and so forth. Whereas, for a high speed operation, these electrodes are no longer lumped electrodes, but you should consider them as a travelling wave electrodes. That means, let me redraw so that means the electric field that is impressed upon that is distributed on these electrodes as travelling waves. So, let me just as an example, let me take that electric field is distributed as follows. That means there is, see, okay, let me in order to analyze these electrodes, you have to treat them as microstrip lines. These are effectively waveguides of microwave frequencies, where the microwave can be guided along these strips. Typically, you need to have a load and your source, microwave source at the other end. So, this is microwave source of certain frequency, and the guided wavelength, and so the properties of these microstrip lines will determine how the field is distributed, and at every point there is a different value of the electric field. So, at each point the electric field is varying. So, you need to calculate the refractive index variation at each step and then calculate what is the total phase shift. So, you can use a step or staircase approximation. For the applied electric field, and then calculate what is the phase shift. The phase shift could be very rigorously calculated by considering the wave propagation along the microstrip lines and light wave propagation along them, and the velocities of course are different. Microwave and optical velocities of the medium of the wave in the medium are different, and so using rigorous techniques you can analyze what is the propagation properties of these and their electro-optic properties. So, this subject of applying or combining microwaves and light waves is called the microwave photonics. It uses microwave techniques for application to light waves, optical problems, and optical techniques to study microwave properties of the devices. Typical applications are high speed communications, high speed fiber optic communications, where you modulate the light wave with a high speed microwave, and also the other application of using the light waves for microwave applications is for beam steering applications, beam forming or steering an antenna. For example, if we form a beam steering circuit with optical fibers, you can obtain delays that are required for beam forming an antenna. These could also be obtained by using integrated optical devices like waveguides, delay lines and interferometers to achieve the required delay, so that the antenna beam could be directed in some particular directions. So, we will look at a few more details about this electro-optic effect before we conclude. So, the electro-optic effect is heavily dependent on the direction of the application of the fields. The simplest case what we have considered is called the over the electrodes configuration. So, I am drawing the cross sections where you have a light wave below. Let me simply say lithium niobate based device, where this is the optical waveguide typically formed by diffusion of impurities like titanium into lithium niobate. A few traces of titanium metal diffused into lithium niobate can form these optical waveguides. And of course, I am showing you only one waveguide. The electrode could be adjacent to this, or first let us take the over the field. So, the electrode could be placed over this. This is the electrode, metal electrode with a ground electrodes at some other point. So, the field there, the microwave field or applied electric field could be said to be forming a field lines as follows. So, if you are considering a light wave of TE mode, which is oriented in this direction, and microwave is oriented perpendicular to this. This is one direction of the optical field, this is the direction of the microwave field in the over the electrode configuration. Similarly, you can also think of the electrodes which are aligned across the waveguide. So, in such a configuration you have electrodes placed like this. Let me say this is the microwave waveguide, and you can consider the electrodes placed adjacent to that. So, let us say this is the ground electrode, this is the signal electrode, and the fields can be expressed to be parallel to the direction of the field. This is E microwave field, and if you are considering TE mode, E optical also is in this direction. So, there are various configurations that are possible, and also you talk in terms of the crystal orientation. So, crystals are defined in terms of their orientations, in particular the direction of the way the crystal is cut defines the axis. So, in the classical optics you talk about the ordinary refractive index and extraordinary refractive index. So, based on the cut orientation and propagation of the direction of the light wave, we can choose the we have to choose the appropriate coefficient and calculate the refractive index variation. There are many other practical issues. For example, a metal cannot directly be in touch with the optical field. So, we need to have a buffer layer before we do that. In the case of electrodes which can be placed over the waveguide, you form a buffer layer and then apply the voltage. This could be buffer, but that would isolate the field a little bit, and you have to account for the variation of the field in the buffer layer. It may increase the amount of voltage that you apply to the electrode. We will go to another effect. One more application we can think of with electro-optic is the electro-optic switches. When we discussed about the directional couplers, we considered two parallel waveguides and said that if you launch light into one of the waveguides, it is possible to design the directional coupler such that the signal comes out of the opposite port. So, this is due to it can be called as evanescent coupling. We have studied this using the coupled mode theory. Now, suppose we would like to create a situation where the light launched into the first port exits out of the first port itself. So, in order to do that, one of the simplest ways that you can think of is to have a long directional coupler of double the length, so that the light goes back into the first port. So, the previous state could be called as a crossover state, and the present one can be called as a bar state. But the length of the device could not be changed easily once you fabricate, that you do not have any control on the configuration. So, we can think of a possibility where you apply voltages or use the electro-optic effect, so that this function could be realized. So, the requirement here is we should change the refractive index delta n such that within half the length of this device the power is exchanged to the other port, and in the remaining half of this the light goes back to the first port. So, we can think of when the delta n is, or let me put it, let us say that we are changing the delta n with applied electric field or voltage. So, when there is no voltage, the design is for crossover state, and when you apply voltage, the refractive index changes such that it switches into the second waveguide and goes back into the first. So, a crossover state for certain amount of voltage, say for example 5 volts. So, this could be called as an electro-optic switch. When the voltage is 0, it is in the cross state. When the voltage is applied, it is in the bar state. Once again, you can think of several configurations and other technical issues like the switching speed and so on and so forth. There are many other variations of this electro-optic switches, like the split electrode configuration, and then also practically speaking there are tapered sections you have to take care when you want to couple the light into and out of the device, and so on and so forth. So, it is also possible, as we have seen in one of the earlier talks, that you can cascade these electro-optic switches to make higher order switches. This can be called as a 2x2 switch. And you can cascade them such that you can get higher order switches. Let us say this is a, I will use a block this time, and this is in 2x2 switch, 2 input ports and 2 output ports, and it could be in the cross state or bar state depending on the voltage that you apply to this. We can call it as a control voltage, and you can cascade 5 of them like this. And obtain a 4x4 switch. But as discussed earlier, it may not be possible to get any combination. Say, let me say this is a signal 1, signal 2, signal 3 and signal 4, or port 1, 2, 3, 4, and output ports T1, T2, T3, T4. We can work out a combination of switching states. For example, you have switching states V1, V2, V3, V4 and V5. So, you can program these values of the voltages such that you can obtain a proper switching configuration. Now, let us go to another important effect called the Acousto-optic effect. Acousto-optic effect essentially implies the change in the refractive index of the medium with applied stress fields. in a very simple way we can say by applying the pressure variations or sound variations. Let us simply make the stress strain fields. So, application of the creation of these stress fields could be obtained in various ways. One of the important ways that is done in acousto-optic devices is to use what is called an IDT pattern, interdigitated pattern. Interdigited electrode. So, a typical interdigital electrode looks as follows. You have a combination of high and low voltages like this. So, I will draw in a very simple way. So, let me say these are the electrodes which are interconnected, and this I will replace the double lines with single lines. All these are electrodes of certain thickness. Typically, these are connected to the opposite polarities plus and minus. So, plus voltage is applied to these electrodes, alternative electrodes, and negative or minus voltage is applied to these electrodes, and this is varied rapidly at a certain rate by applying an RF voltage. So, a microwave could be applied to this to alternate these plus and minuses at a certain rate. So, due to the distributed nature of these electrodes, it is possible that the field across this is changing and can create a propagating wave. In the electrode there is a wave which could be launched onto the crystal. Suppose if whole of this IDT pattern is printed onto a acousto-optic crystal on the surface of a acousto-optic crystal, it is possible to create a strain wave depending on the voltage that you apply. So, the property of the material is we are trying to create a stress field or a strain field by using a electric field. Electric field is only incidental to create this, but ultimately the effect implies the strain field that is propagating on the crystal. This can be called as a surface acoustic wave. Surface acoustic waves are waves that propagate on the surface of the crystal, and they have certain properties governed by the acoustic equations and so on and so forth. For today's discussion, we can just simply say that there is a stress variation of on the crystal due to the, so it could be either in terms of the phase change of the acoustic waves or intensity changes of the acoustic waves. But ultimately we are interested in refractive index varying with the stress field. So, since this is a periodic property, we can assume that the refractive index is also periodic and effectively creating a grating. So, an optical grating is created by the surface acoustic wave, that is the final effect. And once you have a grating, we know the properties of gratings, and let me identify for the time being with a slab waveguide. You have a slab waveguide on which you will propagate a surface acoustic wave. So, the optical field and the surface acoustic wave are confined to a certain thickness of the waveguide, and the confinement of the light field is only in the depth direction. It could of course spread in the across the waveguide, and we can also think of creating a channel waveguides over which you can create gratings. So, you can create waveguide gratings by using surface acoustic waves. These waveguide gratings, as we have seen earlier in one of the initial lectures, have several important applications. So, in the simplest case we can think of delta n as a function of strain field. So, delta n is a function of strain and is a periodic function, that is an important requirement. Delta n is a periodic function of S. Delta n z, let us call it. So, there are many applications. One of the important applications of the waveguide gratings is to deflect light across different directions. Just to give an example, we have a device with an Acousto-optic cell, so called Acousto-optic cell. Just a minute, I am just drawing a IDT pattern. Let us consider this as a very crude IDT pattern. We can apply RF to this and create a surface acoustic wave in this. So, if you launch light across this grating, Acousto-optic grating, you can expect the light to be deflected in particular direction based on the grating pitch. So, the grating pitch is defined as the distance between two points of high refractive index or low refractive index. So, I will call it as a pitch, capital gamma is the pitch. So, the gratings could be analyzed in various ways, in particular by using the coupled mode formalism, where there is a forward propagating wave and backward coupling wave. So, the grating theory is based on the coupling between a forward propagating wave and a backward propagating wave. There are many other applications we have discussed in the earlier or we may be discussing in the future course of action. The speed of the Acousto-optic devices or the dimensions involved, the grating pitches involved is a very interesting relationship. As you know, the sound waves are about 10 power 5 times slower than light waves. The sound waves in crystals are 10 power 5 times, typically 10 power 5 times slower than the light waves. So, you can think of in terms of velocity, I am talking in terms of the velocity of sound wave compared to velocity of light waves. So, and we can use the relationship with the frequency and the wavelength. Velocity is product of frequency and wavelength, and we can use this relationship between the sound waves and light waves to interlink the dimensions of acoustic devices and optical devices. In particular, I would like to mention that the light waves are of the orders of wavelength of light 1 micron typically. Visible lights from 400 to 700 nanometers of the orders of 1 micron, and this is optical, and sound waves are of the orders of a few millimeters and centimeters, say 1 centimeter. So, because of the difference in the velocities, the wavelengths are of the orders of 10 power 5 different. Similarly, we can also think of linking these light waves, sound waves and microwaves, where microwaves have frequencies of the orders of a gigahertz, 1 gigahertz of the 10 power 9 hertz, and once again the velocities are similar, not exactly same, but of the light waves and microwaves are of the same order 10 power 8 meters per second, and so we can use this process, these relationships or this phenomena of acoustic waves to relate microwaves and light waves. This is an additional dimension to the microwave photonics. So, the acoustic waves can link microwaves and light waves easily. So, now we will look at other important phenomena, in particular the magneto-optic effects, and we will highlight that we are dealing with highly anisotropic properties compared to other earlier fields that we saw, like the acoustic effects and the electro-optic effect. Of course, most of them are anisotropic, but we can find the maximum anisotropy with magnetic materials, and they could be used for many other important applications, like in optics and in integrated optics we need control of polarization, and control of phase. All this could be very well achieved by using magneto-optic effects. In particular, if we are given a small relationship, for example delta n is a function of the magnetic field H, we can estimate what is the change in the refractive index, and of course it is very important that we take note of the direction of the magnetic field and the component of the refractive index that is affected. And this could be used in many ways. For example Faraday rotation. The rotation of the polarization state of a light wave can be achieved by applying magnetic fields. So, I will give a small example of a device which uses magneto-optic effect. Let us consider typical devices or garnets, yttrium iron garnet or yttrium aluminum garnet. These are some of the materials which have got magneto-optic effect, and like in the case of acoustic waves we can also think of magnetic waves. They are called the magnetostatic surface waves. So, magnetostatic surface waves could be created and propagated on a crystal like this, magnetic crystals, and some of them have good optical properties. So, you can have a good interaction between the electric and magnetic properties to achieve some good functions. So, a magnetostatic surface wave also could result in a grating like device through which the light could be propagated. So, once again the magneto-optic effect could be a function of RF to create gratings and so on. So, another important way that we can use this magneto-optic effect is to coat a magnetic medium on top of an optical waveguide. Let us assume this is an optical waveguide. In a cross section it is like this, and you can coat magnetic medium on top of that. This may be a isotropic medium where it may not affect the properties, optical properties much, but this could be a magnetic medium. And let us say if we are controlling the magnetic properties by applying voltages. So, the magnetic properties are dependent on the voltage, and so we could control the propagation of light wave within these. This is one of the ways which we can say polarization state can be controlled. Can be achieved. So, another important category of effects that can be used to control the properties of integrated optical devices can be called as nonlinear effects. Nonlinear optical effects. In the previous case the fields have been applied externally, whereas as we may intuitively guess that the properties of the medium can depend on the light wave that is propagating, because the light wave has got electric fields and magnetic fields associated with this. So, the electric field and magnetic fields are associated with the light wave. So, if the intensity is sufficient enough, this could have a very dominant effect on the properties of the medium, and this could be called as nonlinear effects. Essentially depending on the E and H fields of the light wave. Here we are considering, we are not considering the fields that are applied externally, but it is also possible to launch light into the waveguide and control the properties, and the signal could be a different light wave. So, we will just consider one or two important cases and important applications. So, there are several effects, most of them should be dealt with by using the polarization of the medium. P is the polarization of the medium, which could depend on the electric field. So, if you look at the displacement vector, you can substitute this into the Maxwell's equations to derive the nonlinear equations. So, P is given as epsilon, let us say epsilon 0 is the electric permittivity of the uniform medium or the free space, and chi are the coefficients, susceptibility coefficients, electrical susceptibility, say of different orders, psi 1, 2, 3, 4, etc. And E are the electric fields, is the second order and is depend on E square, typically written with a colon to say that this is not only E square, but various components of the E are combining. For example, you have 3 components of the electric field and various combinations Ex, Ey, Ez, not exactly multiplication, but Ex and Ey could result in the second coefficient, and these are all typically the tensors, susceptibility tensors. They are expressed in terms of E cross E and so on. So, depending on the coefficient that we use, we talk about the nonlinear effect of that particular coefficient. So, D, or let me, this is P and D is expressed in terms of epsilon naught E plus P. So, if we look at the wave equations on the right hand side, we have been getting a linear term, but whereas it is also possible to obtain squares and cubes of the electric field on the right hand side of the wave equation, which implies that there is a nonlinear phenomena. The equations are nonlinear. So, there are several effects that we can consider, in particular refractive index dependent depending on intensity, on the light dependent intensity. So, delta n is a function of light intensity. So, a simple effect that you can think of with such a phenomena is, if you take an optical waveguide, normal course of action when there is no nonlinearity, when there is no high intensity light incident into the waveguide, the delta n is not dependent on the, not much dependent on the intensity, but now it is dependent on intensity, and we know that we have a mode spot of a certain shape. So, the refractive index is also a function of x comma y. So, this is resulting in a graded index waveguide, and the mode spot is modified, including its propagation constant. Propagation constant for the graded index, refractive index is different, and so continuously the propagation constant is being modified as the light propagates along the waveguide. So, at each point you have a different propagation constant, or we can say that the beta is depending on the propagation direction in some complicated way based on the refractive index variation. and you can think of the phase shift and so on. So, the phase change can be studied as light propagates along the waveguide. Similarly, in nonlinear optical, one of the important nonlinear optical effects is called the second harmonic generation. So, you have a waveguide into which you launch optical light of certain frequency omega, and the output could be of frequency 2 omega. So, this can be explained by using the second order effect, where you have an e square term if each of the terms e are expressed in terms of e power I omega t, a multiplication factor leads to e power 2 omega t. This is how second order effects could be explained, but it is also possible to develop a coupled mode theory relating the incident field, the second harmonic field and the total excited field to study how the coupling from the various components of the electric fields can take place, and in particular we can emphasize on what can be called as a phase matching. In the case of optical waveguides, in the directional coupler for example, we have seen that the coupling between the two waveguides is possible only when certain condition is satisfied, when delta beta has certain values, integral multiples of some values. Similarly, we can think of these nonlinear effects, in particular the second harmonic generation is possible when there is a phase matching between the light propagating in different directions. So, I would just like you to note down that phase matching is an important factor in the nonlinear optical, in realizing the nonlinear optical effects. So, there are many other effects that can be used to control the properties of optical waveguides. In this discussion we have considered only properties which are dependent on the external. We have not considered properties where there is interaction between the light and matter. For example, the electrons of the crystal, or if it is a semi-conducting material for example, there will be interaction with the light and matter leading to many other effects like the electro-absorption effect, or control of the optical devices by applying by injecting charge carriers into the active region and so on and so forth. So, this will form an important domain of integrated optics that can be termed as optoelectronic integrated circuits, which is slightly beyond the scope of the present course. Thank you very much.